Welcome. Today's lesson is entitled Rational Expressions Day 1. This is very much a skills-based lesson, so we'll be talking a lot about the do's and don'ts with manipulating and performing operations on rational expressions. So let's dive right in. I guess the first order of business is to define what a rational expression is, and I guess the short version of the story would be a rational expression is a fraction, as you see over the course of this entire lesson. But here's what I have on my sheet, and then we'll put an example off to the side as well. So it is a quotient of two polynomials. And there's one little caveat to this, so I'm going to write that in as well. And it deals with the denominator. So it must be at least a degree 1 in the denominator. And I'll tell you what I mean by that in just a sec. But get that in place if you would. And then here off to the side, we'll just write an example of what a rational expression is. And anytime I've got that fraction line going with a polynomial in the numerator and a polynomial in the denominator, that would be this family of expressions. And something like this, a little quadratic numerator. And it has to be at least a degree 1 in the denominator. So it can't be a constant in the denominator, which would be a degree 0. So anything from linear up above would do the trick, and so something like that would be fine. So that's an example of a rational expression, and we're going to do a variety of things with these rational expressions over the next 2 lessons. We'll do some simplifying, we'll do some multiplication and division, we'll do some addition and subtraction, and we'll do some simplifying of more complicated rational expressions as well. So let's start the process here. It looks like the first order of business would be to talk about simplifying a rational expression. And so what that means, just like it does with fractions, is we're going to reduce. So we're going to reduce the expression. And here's going to be the key. So there are no common factors. You'll hear me talking about that buzzword quite a bit over the course of this lesson in the numerator and denominator. All right, great. And we'll do a little investigation or 2 beforehand to kind of get that rolling. But it's going to be all about factoring today. Factoring and knowing when to cancel things out and when not to. But before we actually get into that, we do need to take a look at the example 1 that's on your sheet. And rational expressions are very unique in one particular way. And it deals with what I'm after in example 1. So it reads, find all of the numbers that are excluded from the domain. So what I mean by that, as it says in parentheses, is give me the numbers for x that are going to make the expression undefined. Well, when talking about a rational expression, or a fraction in general, like this, and like this, and like this, we have to be concerned about one particular restriction. And I'd ask you to think about it. What is the one restriction when dealing with the fraction? What do we have to be concerned about? And you probably remember this from middle school or your previous classes, but what we really need to be worried about is I cannot divide by 0. So the denominator being 0 causes the value to be undefined. It causes us not to be able to do the operation at hand. And so the question is, are there numbers that would go in place of x that would make the denominator 0 and ultimately have to be excluded from the domain in order to make us do the calculations that are appropriate? So let's do just example 1a, and then I think we'll go right to the conclusion there, and then we'll try b and c after the fact. So here's what I'm thinking with this one. As I look at this fraction and looking at all the numbers that I can put in place of x, it's great, except I have a problem if x is 3. Because if x is 3, then I have 3 plus 2 in the numerator, which will be 5, and then 3 minus 3 in the denominator, which would be 0. And if I tried to do this calculation, it's simply not possible. In fact, I have my calculator at hand here. I'm just going to be really quick with this and just show you exactly what I typed in, or exactly what I put in on my paper. And 3 plus 2, and then divide by, and then the denominator is 3 minus 3. And as you, of course, see, that operation is just not possible. I can't divide by 0. I can't do that and get an answer. And so as a result, the value of 3 must be excluded from the domain. So that was what was undefined right there. X can be any other number. If X is any other number in existence, I can do those operations and get an answer. But if X is 3, I simply cannot do those operations and come out with an answer. So I guess the conclusion, and then we'll quickly do B and C, the conclusion really very simply is this. Values that make the denominator 0 must be excluded from the domain. So put that in place if you would, and then we'll check that out in just a sec on B and C. So excluded from the domain. All right, perfect. So the numerator is sort of irrelevant, because if the numerator is 0, 0 divided by anything other than 0, but 0 divided by anything is going to give us 0. But it's the denominator that I have to be concerned about in the fraction. And so in this particular case, I've got this quadratic in the denominator in standard form, and standard form doesn't really help us. But if I go ahead and factor it, and it looks like just x minus 5, x minus 1, then I can see which values for x would make the denominator 0, and hence the overall expression undefined. And so those particular values need to be excluded because I cannot put them in for the variable. And so we would just say x can't be 5 and x can't be 1. So I'm going to box these up as I go through this lesson, hopefully. And so there's that one, and there's that one as well. Awesome. So letter C, same deal. This one's a little harder, obviously, because I've got that 2 in front of my quadratic trinomial. But if I'm looking for the values of x that are going to make the denominator 0, standard form is not very helpful, but factored form sure is. So I'm going to make my 2 binomials underneath. I'm going to put a 2x there and an x there because those are going to have to multiply to the 2x squared. And to get to negative 21, it's either going to be a 1-21 combination or a 3 and 7 combination. I think I'm going to go ahead and put a 3 and 7 in. And looks like this, just from my outside-inside perspective, is going to be plus and then minus. And you can kind of see that here. There's a negative 14x. There's a positive 3x. And those combine, of course, to negative 11x. Perfect. So what that means, once it is in factored form, then I can decide, well, these are the values that are going to make it 0 and are going to have to be excluded from our domain. So if we set this to 0, it looks like we would get negative 3/2. And so x simply cannot be negative 3/2 there. That would make the denominator 0. And it looks like x can't be positive 7 because same thing. If you put 7 in for x, it would make the denominator 0. All right, so keep that in mind as a restriction on what values we can put in place of the variable as we work with these rational expressions. Perfect. Let's move on to the next piece. So before we do get into the simplifying component of the lesson, we just want to kind of figure out when can we reduce, when can't we reduce, when is it legitimate and when is it not. So I came up with a very quick investigation, just very concrete, just so we can see it. And let's go from there. So letter A, 6/9. If I said to you, reduce 6/9 for me, I think without blinking an eye, you would probably tell me 2/3. And the reason you would tell me 2/3 is because of the way it factors. 6 can be written as a product of factors 2 times 3. 9 can be written as a product of factors of 3 times 3. And what happens, everybody, and do it on your sheet there, those 3's can cancel right on out. It is what's called a common factor. And so they cancel out, and so 6/9 is equal to 2/3 because the 2 and the 3 are the remaining factors after the 3's cancel. And so yeah, you can definitely do that. That is completely legitimate. But as I move over to letter B, what if those same 3's, instead of being separated by multiplication, were separated by addition? Is the left side of this equation equal to the right side? Well, just some quick mental arithmetic. 2 plus 3 is 5. 3 plus 3 is 6. Is 5/6 equal to 2/3? No, that's definitely not the case. But you would be surprised when it gets more abstract and we start putting in variables, how students want to just go ahead and cancel out those common things, even though they're not common factors. So that is your primary challenge for this lesson and all the types of problems that come with it. Can you determine when it is okay to cancel out something from the numerator and denominator, and when it is not okay to cancel out something from the numerator and denominator? So let's put that in. So terms in the numerator and denominator can only, and this is the key, can only be canceled out if they are common factors. And again, that is our buzzword of the day. So common factors. All right, so let's see that in action a little bit as we go through the process. I'm going to go ahead to my next board here. And so it's always good for me to put these in as reference. Obviously, I'm going to read through them, and you have them to look back on if you need. But as we work on the first component to rational expressions, meaning the simplifying, what are the strategies that we would incorporate? So it says on your sheet, number one, write the numerator and denominator as a product of factors. Absolutely. That's what we're going to be talking about. And then number two, once things are written as factors, then and only then can we cancel out those common factors in the numerator and denominator. So as we look at example 2, and the instructions are pretty simple, just simplify the rational expression, and then there's this the secondary piece about finding the numbers that must be restricted from the domain. Very simply, before we think about let's cancel stuff out, the first thing you have to do is factor. So don't think about canceling just yet. That's a secondary piece. The first thing you want to do is say, can I factor the numerator? And if so, do it. Can I factor the denominator? And if so, do it. So as we dive into letter A, I kind of look at this up here, and it's just two terms separated by the addition symbol. So it's a quadratic in standard form. And I'm looking sort of as a greatest common factor pattern where I can pull out a 3 from each of those and an x from each of those. So it looks like the greatest common factor from my perspective is going to be 3x. And when I factor out a 3x, it looks like I would have a 5x and then an 8 on the back end, so 5x plus 8 as that binomial factor remaining. Good. And if what you see happening here is this was the standard form of the polynomial in the numerator. This is the factored form of the polynomial in the numerator. Perfect. All right, now the denominator is sort of interesting because it's only one term. So we're not really talking about factoring in any type of traditional sense because it's only one term. But if you look at it, it is 3 times x squared. So there is multiplication already embedded in here. And in fact, x squared is also multiplication because it's x times x. Now you don't have to write that if you don't want. If you can kind of see this without it, then more power to you. But I kind of like that piece because then we've got 3 factors in the numerator, 3 times x times 5x plus 8, and the denominator, 3 times x times x. So at this stage, it is in factored form, and now we look to do the next piece, which is cancel anything in the numerator and the denominator that is the same. The 3's, it's a common factor. These x's, common factor. And so when I do that, it looks like I'm left with the 5x plus 8 over x. Now here's the million-dollar question. Can we cancel out these x's right here? I have one in the numerator, one in the denominator. What do you think? Well, unfortunately, the answer is a no, without question, because the x is actually not a factor of the numerator. It is part of this binomial, but it is not a factor of the numerator. And so you cannot cancel that. That's going to be the key. It's separated by that addition symbol. It is part of the overall factor. So this is your final answer. And as I said, that's going to be the primary challenge for us is when can you factor and when can you not factor? Or when can you not cancel, excuse me. Awesome. Well, there was that secondary piece to this. It did say find all numbers that must be restricted from the domain. So we always go back to the original, never the simplified version, always from the original because that's where it's coming from. And in this case, if I think about 3 times something squared equals 0, just to move this along a little bit, I hope you do agree that x can't be 0 because 3 times 0 squared would give me 0 in the denominator. So this 0 must be excluded from the domain. Perfect. Now let's get into letter B and sort of asking another question beforehand here. I guess I would ask you this. Those 4x to the fourths, as nice as they are, one in the numerator, one in the denominator, do they just cancel out? And the answer is no, because 4x to the fourth is not a factor of the numerator. It's not a factor of the denominator. I haven't factored anything yet, so I shouldn't be thinking about canceling anyway. So let's start this a little bit. And if you want to go ahead of me and work on factoring, that's great. Because that's not the focus of this lesson, I'm going to do factoring a little quicker within the context of each problem. But I look at the numerator here, and it looks to me we've got a nice GCF to be pulled out there. I'm thinking a 2x squared should be pulled out. And once we pull out that 2x squared, it looks like I have a 2x squared plus an x, and how about minus 3 on the back? Perfect. And then I look to the denominator, same idea, to factor it. Same one actually comes out. It looks like a 2x squared can be factored out. And in this case, I'm getting a remaining quadratic trinomial of 2x squared. How about a 13x and then plus 15? Okay, now that's looking really nice. I moved forward in the factoring process, and there's probably some things we can do right off the bat. I am going to hold off on that for a moment, though, because before I pull the trigger on canceling stuff out, I do want to ask myself, have I factored everything completely? And as I look at these quadratic trinomials, one in the numerator and one in the denominator, it does look like we can go further with those. So should be more and more comfortable with factoring these types of expressions, especially with the number in front of the x squared. And let's see if you can do that. Give you a moment. If you want to pause the video and give it a try, I would encourage you to do that. And then I'll go ahead and write in what I have on my sheet. So it looks like it has to be a 2x and an x, right, to get that 2x squared. And this isn't too bad with a 1 and a 3 on the back. But it looks like I've got a plus 3 here and a minus 1. And I believe that's what's going to give us the outside and inside combining to that plus 1x. So negative 2x, positive 3x, that makes positive 1x. Perfect. I do the denominator as well. Again, just good old-fashioned factoring. We need two numbers that are going to multiply to 15, and I need the outside and inside to combine to that 13x. And you can use my method. You can just use trial and error. But ultimately, I think we're going to get something along these lines right here. And if I verify the outside and inside, looks like I have a 10x and a 3x, and that looks like it's going to work nicely. So if you look, I've changed from standard form, my bad, to factored form. Same with the denominator, standard form to factored form. Now that we've got it in the form we want, we can start thinking about common factors. The 2's, absolutely. Both factors of x, absolutely. 2x plus 3's, no doubt about it. And so what that would leave me with at this stage is x minus 1 over x plus 5. Now the key question I would have for you here is, can we cancel out the x's, one in the numerator, one in the denominator? And I'm hoping you're getting better and better at seeing this, that it has to be a definite no, because the x is not a factor of the numerator. The x is not a factor of the denominator. And so that's our final answer in terms of the simplified version of this pretty complicated rational expression that I gave you. Now before we move on to the next piece, we do want to answer this last part of example 2. Find all the numbers that must be restricted from the domain. So we look to the denominator, but remember we always look to the denominator of the original. Okay, even though we simplified this, this really came from this piece right up here. And so these restrictions carry over into the simplified version that you see here. Now standard form, not great, but we did factor it, of course. And as I look at some of the variable factors here, I start to see the things that would make the denominator 0. Now we don't have to worry about this. This constant doesn't do anything with restricting the variable. But I notice here x can't be 0, because 0 squared would give me 0. In terms of this factor, it looks like x can't be negative 3/2, because it would make that factor, and hence the entire denominator 0. And x can't be negative 5. So those three values, again, even though we don't see that here, it manifested itself in the original, and that's where we're looking. So those are the restrictions on the domain. Perfect. Okay, so we did some simplifying. Now let's get into the multiplying and dividing. Same idea. I always like to give you a little reference to come back on. So these are the strategies that I would use to work with multiplying and dividing, I guess, these rational expressions. So number one, again, all comes down to factoring. Factor, factor, factor. So factor each numerator and denominator. Because it's going to be all multiplication straight on through, we can cancel out common factors. And then if you remember from middle school, just at the end of the day, we just multiply numerator straight across and multiply denominator straight across. Okay. Well, example 3. It reads, perform the operation with the rational expressions. Find all numbers that must be restricted from the domain. Perfect. Big multiplication symbol in between, so it's this rational expression times this rational expression. And very simply what I'm going to do is rewrite each of those in terms of its factors. So I'm going to factor the left numerator, the left denominator, the right numerator, right denominator. Cool. Now again, you're more than welcome to go ahead of me or pause the video and see if you can factor yourself. I just noticed this is a difference of 2 squares, and so I'm going to get that going right away as 3x plus 5 and 3x minus 5. Left denominator seems to be just a quick greatest common factor situation. So pull out the 2, get x minus 1. The right numerator looks to be also a difference of 2 squares, so how about an x plus 1, x minus 1. And lastly, looks like the right denominator, pulling out the 2 and getting a 3x minus 5. Okay, now we're in a good position in terms of multiplication. And you notice it's this times this, times this, times this, and denominator same thing. It's all just multiplication straight on through. So anything in the numerator and denominator is fair game. 3x minus 5's, goodbye. X minus 1's, good riddance. I don't think there's anything else, although I guess I would ask you this. Can we cancel out the 2's? And no, we can't. And the reason, of course, is they're both in the denominator. So we can only if it's in one in the numerator, one in the denominator. So at this stage, we just go to my strategy number 3, and that's just multiply across. Now, don't feel like you actually have to FOIL this out. It's just pushing it straight across as a product of factors in the numerator. Obviously, the 2 times 2, which is just left in the denominator, that I could at least quickly do. But that would be it. Perfect. Now let's talk about the restrictions from the domain. Again, I don't look here. I look at the original. That's the key. Specifically in this case with multiplication, I'm going to look at these denominators. And standard form, that's not as helpful, but factored form, here's where I'm going to be looking, and here's where I'm going to be looking. And I can tell just from those 2 pieces that it looks like I have 2 values that are going to be restricted from the domain. It looks like x cannot be equal to 1 because of that right there. And it does look like x can't be equal to 5/3 because of this factor in the denominator there. And so those are your 2 restrictions on the variable. And that looks pretty good. Let's go ahead and solidify that with letter B and see what you think, and then we'll get into the division. So once again, before you do anything with multiplication as it's written in standard form, I literally just rewrite the two fractions with the multiplication in between using factored form. So hopefully you're getting quicker and quicker with these factors. This is x minus 1, x minus 1. This has a GCF of x and then x squared plus 1. This has a GCF of 4 and then an x squared plus 1 as well. And then the denominator looks to be x plus 2 and x minus 1. So just 4 parts, 4 factoring methods. Looks great, and it's all multiplication. So let's be very clear on that piece. We factored. Now we can cancel out common factors, and then we'll just push things across. So x minus 1s are going to be gone. X squared plus 1s also gone. And I think that might be it. Okay, so what's left? Well, the 4 and the x minus 1 are left in the numerator. And the x and the x plus 2 are left in the denominator. If you distribute it in each case, you're more than welcome to do that, but it's not necessary. And that's looking pretty good. So we need to get onto the restrictions here, and then we'll try some division with this. So we look for the denominators. Again, always at the original. So I'm looking at what's going to make that 0. I'm looking at what's going to make that 0. Because they're in standard form, that's not super helpful, but I already factored them, so now I can see how it resolves itself. And I look at those factors and start to think, well, what would make that factor 0, that factor 0, that, and that? And so we can start getting some restrictions going. First and foremost, anytime you see a factor of just x, that means that 0 would make it 0. So in this case, have to exclude 0. This is an interesting one here, and I'm just going to do this more quickly off to the side. I promise I'll be quick on this. But you are kind of asking yourself, what would make that factor 0? Because I would have to exclude it. And if I solved for x here, I would get x squared equals negative 1, and then I would square root and square root. But is there any, when I do the square root of negative 1, is there any real number that's going to that we're going to get as an answer? And I don't think so. So in reality, if you take any number, real number, squared, and add 1, you're not going to be able to get 0. So this factor didn't produce any restrictions. Okay? But the negative 2 from x plus 2 and the positive 1 from the x minus 1 absolutely do. And so we see that. So multiplication, hopefully the two examples help you kind of work through the process. If not, division hopefully will do that as well. So let's get right on to the division. And just kind of thinking back to middle school potentially, what must you remember to do first when you divide rational expressions? So think about dividing fractions, what you ended up doing way back when. And here's what I wrote on my paper, and hopefully you'll agree with this idea, and we'll see it in action in just a sec. But we flip the second expression. Flip means basically changing it to its reciprocal. So flip the second expression and change that symbol to multiplication. And this goes back to the idea, if you remember working with fractions in previous classes, dividing by a fraction is the same as multiplying by its reciprocal. And so that's what we're going to play out here. I'm going to change this to multiplication, and I'm going to change this to its reciprocal. So never the first one, just the second one you flip. So as I actually look at example 4, and I have a feeling the instructions are going to be the same, so perform the operation with the rational expressions, division here, and division here, by the way. Find all numbers that must be restricted. There is a little bit of a catch with this piece, so we'll be careful on that. But ultimately, we're going to treat it in a very similar fashion to what we did on example 3. The one thing I do first here, when I see the division symbol, and feel free to not do this particular step, but I do find it helpful, is I write everything into standard form, but do exactly what I said. Change to multiplication and flip the second expression. That way I don't forget about it, and I make sure that that ends up in the numerator, that ends up in the denominator. So something along those lines right there. Then it's no different than example 3, and I can just run my two fractions, now going from standard form to factored form, and playing it out accordingly. So hope that makes sense. As I go ahead to look and factor this, obviously x plus 3 doesn't factor. Difference of two squares on the bottom. Hopefully, again, you're starting to see the idea and getting quicker and quicker with the factoring. This is a good one right here, everybody, x cubed minus 8. So that's what's called a difference of two cubes. See if you remember that pattern. So that was the small linear and the larger quadratic. Turns out to be x minus 2, and then x squared plus 2x plus 4. Good one. And then the denominator here looks like x minus 4 and x plus 3. All right, so factored form in all 4 parts there. I think we're in really good shape. And let's see what cancels out and go from there. So x plus 3s, they're gone. X minus 2s, they're gone. And I think that might be it. Now remember a couple things, by the way. First of all, this quadratic is prime, so we would certainly look to factor it, but in this pattern, that is a prime quadratic trinomial. All right, and so the only thing I have left actually is that quadratic prime. And there we go. The denominator would be that right there. All right, now we have to take a couple minutes and talk about the restrictions. So division has one more element to it compared to the multiplication that we did in the previous example. And so here's what I'm thinking you should do on your paper. I'm going to circle it, but then I'm going to erase it. But I want you to just very lightly on your paper circle this, and circle that. So again, always looking at the original. And just make a little note off to the side for what you had circled very lightly on your paper. Those are the components of the rational expressions, actually, when you're doing division, that can't be 0. And I'll show you why. You can kind of put the pencil down for a second, and let me just show you what I'm thinking with this. So we have one fraction divided by another fraction. And if I use numbers for a moment, rather than these abstract variables, we can kind of see why these 3 parts of the expressions have to be concerns for us in terms of the domain. So let's start with the bottom left. Why can't that part be 0? Well, if I just put a number and divide that by a denominator of 0, if I do something like this, it doesn't matter what's over here. Because isn't this a number that is already undefined? Isn't this simply not feasible? I can't have this denominator be 0 because this number doesn't exist. So if that's 0, we've got problems. I can't do the operation. Now the new part to this is really this, the right numerator. So I'm just going to start with the number on the left. So I'm going to just make that 1 just for argument's sake. And then here's my division. And what happens if, say, the numerator of that right expression is 0? Is that something you can do? Well, as we already kind of learned, and that's what this is all about, is I can't take any number and divide it by 0, and that's what this is. When all's said and done, that's 0. And so if this numerator is 0, then the whole thing is 0, and I can't divide by it. That division symbol precludes this from being 0. So that part can't be 0. What about the right denominator? So that would be something like anything on the left, anything up above. But what about the right denominator? Well, you know, again, it's just you sort of see it. In a single fraction, can the denominator be 0? No. So you start to see these 3 parts of the rational expression when this is division can't be 0. So what would be really cool is if you take a moment while I'm going to erase in a second, and see if you can get all of the exclusions to the domain here. So I'm going to get rid of this. I've sort of said my piece about that. Again, you have those now lightly circled, and now let's use them. So standard form doesn't help, but factored form of all three parts, that's where we're going to get our exclusions. So there and there and there. So I have a nice good running list going, and I think I'll come right here and do it. And I would say x can't be -2. X can't be +2. It looks like x can't be +2 from here either, but I already have that on my list. Now this is an interesting one. There are no real numbers that are going to make this 0. So this quadratic trinomial actually does not produce any restrictions, just FYI. But again, I do need to look at the top for that. But then I come down here and I think that x can't be 4 and x can't be -3. And those, everybody, would be your restrictions on the domain from this example A right here. Cool. You know, I'm just looking at the time component, and I think what I'm going to do is skip letter B. It's a great one. It's this divided by this, and you do a whole lot of factoring and a whole lot of canceling and stuff like that. What I am going to do, if you have the inclination, I'm going to write the answer up here for you. And if you get a chance and you'd like to, it'd be a good one to do. If you can do this one, really you can do just about anything that I give you with these types of problems. But the answer ends up being this. It ends up simplifying beautifully. Tons of factors canceling out. So that would be the overall simplified answer. And then there are a bunch of exclusions on this. So x can't be 1/4. X can't be -2/3. X can't be +1/3. And x can't be -3/2. So again, it might be worth your time to just try it on your own. If you do get a chance, good little practice problem. And here would be the answers for you. But I'd like to get into the last piece of the puzzle here. It's sort of the first part of what will be a continuation on the day 2 lesson. So at this stage, let's just recap actually. We've done simplifying rational expressions, multiplying and dividing rational expressions, and this ties into the next lesson, which will be, of course, as you see, adding and subtracting rational expressions. So a whole different mindset, and that's what we're going to have to be super careful on. But what do we need to add and subtract two fractions together? As you probably remember from a variety of previous math classes, you need a common denominator. So what I'm going to do is just take a moment and give you just a nice formal way, no matter how abstract our terms are, to come up with a least common multiple of what will be our denominators. And again, here's some strategies for you. Break down each term into a product of its prime factors. Okay, so factoring, but now even a little more specific, putting it in terms of prime. And then what we're going to do is work left to right, and we're going to be a little careful on this, so don't take the redundant factors. And I'll tell you what I mean by that as we go through this process. So example 5, the way it's designed is to find the least common multiple for A and B and C. What I tried to do for you is to be really concrete initially, just with 2 numbers, and then we can start opening it up with more abstract algebra for B and C. So let's start out with this. And I guess I would ask you just from a number sense perspective, could you tell me what the least common multiple is of 6 and 8? What number, what's the smallest number that 6 divides into and 8 divides into? And your answer happens to be 24. 6 goes into 24 and 8 goes into 24, and that's the smallest number where that occurs. Now let me show you how we would get that using these strategies right here. So primes, everybody. So 6 is 2 times 3. 8 is 2 times 2 times 2, all prime numbers. Now here's the idea with this as we look to create that 24, which is the least common multiple. I'm going to work left to right. And if I see a number that happens to be in both lists, then I'm going to tie it together as a common factor. And I don't want to include it twice because that would be a redundancy. I just want to include it once. So the 2 in this list is the same as the 2 in that list. So I tie them together and I take it. There's the 2. So there it is, taken. Then, working left to right, I take the next one, which is 3, and I take this next 2 over here. Remember, these 2's are all part of this 8, so we need all of those 2's. So I take the 2 here, and I take the 2 here. Everyone see that? So this is the redundancy, the common factor. I take it once. There it is. I take the 3, I take the 2, and I take the 2. Now if I multiply all these together, 2 times 3 times 2 times 2, of course, I get 24. Now what would have happened if I accidentally didn't treat it as a redundancy and I took both factors? And if I multiplied another 2 in, you would see I'd get 48. Now 48 is, of course, it is a multiple of 6 and 8. But is it the lowest common multiple? No. So by treating this 2 that's in both lists as a redundancy and as a common factor, you take it once, and now you can get the least common multiple. Awesome. Let's go do a B and C, and I think we can do it pretty quickly. If you factor, you get x plus 1, x minus 1. If you factor, you get x plus 1 and x plus 1. And as I work left to right, I'm just going to think about, is there a commonality to the other list? And in this case, there is. That x plus 1 is tied to that x plus 1. They're the same factor. So I take it once, but I don't need it twice because that would be a redundancy. So there, as the common factor, there it is. Then I keep going. There's the x minus 1 here. Remember, these 2 are part of that single term, so I do need them both. So there's the x plus 1 right there. And that would be it. I can probably write this as x plus 1 squared, x minus 1. But that does it. Great, let's go try letter C and then wrap this on up. Factoring, guys, that's what the whole lesson has been about within the context of rational expressions. And if I factor the 3, I'd get x squared minus 4. And x squared minus 4 actually factors to x plus 2, x minus 2. I'm going to work left to right. There, I'm going to take the x plus 3. Okay, this x plus 2 is common with that x plus 2. I don't need it twice, I just need it once. And then a 3, and then an x minus 2. So I took all the distinct factors. Anything common to both lists, I take it once but not twice. Usually you see the 3 out in front, not that it matters here. But there we go, everybody. If it didn't click completely on this last example, don't worry, because this is how we start our next lesson, talking exactly about these least common multiples and then getting a new addition and subtraction. Well, thanks for listening, everybody. Hope you get some good practice with this, and I hope if any of the factoring or any of the ideas behind the lesson were difficult for you, that you just ask and we can go through it together. Thanks.